Again, welcome to Mathematical Structure for Computer Science, that's CS 113, Discrete Mathematics. So in these lectures, we will continue with our graph theory. And here we shall go through the basic concept of graph and also the graph terminology. We shall discuss about special types of graphs and also bipartite graphs, and also how to create a new graph from old one. So we start with our first definition, definition one, which we have some two terminologies here. So here we said, if we have two vertices, UV, again, in our first lectures on graph, we talk about what is a vertex and what is a graph. So normally a graph, again, consists of vertices and edge, or sometimes we use the term nodes and edge. So the vertices are connected with an edge is more or less like a line connecting two vertices or node together. And we have two types of graph, either directed or undirected. So undirected graph means the edge direction, it can move from vertex U to V or V to U. It doesn't matter the direction. But a directed graph means we have to show the arrow, either we are moving from U to V or V to U, but not both. So here we said that if we have two vertices, UV, in an undirected graph G, are called adjacent or neighbors in G if there is an edge E between U and V. So what the term adjacent means is that if we have two vertices and they are connected together by the same one edge, then those two vertices are called adjacent or they are neighbors. So again, if you have two vertices connected together by one edge, then those two vertices are adjacent or they are neighbors. And also the edge that connects those two vertices, we use the term incident. So we say such an edge E is called incident with the vertices U and V, and E is said to connect U and V. So there's two terminology we are learning here. What is adjacent or neighbors and what is an incident? So again, when we have two vertices connected together by one edge, then those two vertices are neighbors or adjacent. And the edge that connect them together is also referred to as incident. So our second definition here, we said if we have a set of all neighbors, now we know what neighbors means. Either adjacent or neighbors means we have vertices that are connected together by the same edge. So if we have a set of all neighbors of a vertex V of G denoted by N at lowercase v, and here it will tell us the number of vertices connected together, is called the neighborhood of V. Now, if A is the subset of V, which means all the vertices in A, they are also in V, but there are some vertices in V that are not in A. So A is the subset of V. Now we can donate by uppercase N at A, the set of all vertices in G that are adjacent to at least one vertex in A. So here we can say that N at A is equal to union, where we have the lowercase v belonging to A, N at lowercase v. Again, that gives us the number of the vectors. So our next definition, the new terminology we're going to learn here is what is a degree of a vertex. So a degree of a vertex, especially in undirected graph, is the number of edges connected to the vertex. But if it's a directed graph, then it will be the number of edges that is going away from that vertex. Because directed graph, we may see an arrow, whether the edge is coming to the vertex or is going away from the vertex. And we will discuss that later on. So for now, the degree of a vertex in undirected graph is the number of edges incident with it. Remember, the term incident means the edges connected to the vertex. except a loop. Now, when we have a loop, it will be 2. So a loop at a vertex contribute 2 to the degree of that vertex. So if I have a regular edge, then it's 1 degree if it's only 1. If I have 1 loop, then it's 2 degree. And we'll see an example. So this is a good example. Here we say what are the degrees and also the neighborhoods of a vertices in graph G and H. Now we know degree means, especially an undirected graph. So these 2 graphs are undirected. There's no any arrow indicating where the graph is, the edge is going towards what vertex. So this is undirected graph. So the degree of the vertex in undirected graph is the number of edges connected to it. And also the neighborhood, which will be the number of vertices, the number of, again, vertices that we use the term adjacent, the same vertices that are connected together, the number of neighborhood they have. So let's go first. We are going to start with what is the degree of a vertex A from G. We say it's 2. Why? Let's look at A. A have edge towards to F, and A has another edge towards B. So A have only 2 edges, so the degree is 2. Now, what is the degree of a vertex B? Vertex B, we have B to C, B to E, B to F, B to A. So that means we have 1, 2, 3, 4. We have 4 degree. So that's 4. And also C is 4. We have C to D, C to E, C to B, and C to F. So that's 4 also. And what F also is 4. We have F to E, F to A, F to C, F to B. So that's 4. So again, the degree of a vertex in undirected graph is the number of edges connected to it. Now let's look at degree D. They say it's 1. Let's see. Degree D is only 1. We have only 1 edge going to C from D. Now degree G. Vertex J doesn't have any edge. So the degree of vertex J is 0. There's no any edge connected. And there's also no loop. So now let's look at the neighborhood. So the neighborhood also, we can go by each vertex. So as we said, the terminology of neighborhood means the vertex that is adjacent to whatever vertex they are adjacent to. So let's say vertex A is adjacent to what number of vertices? That's the neighborhood. So if I'm in vertex, what's the neighborhood of A? It will be B and F. So the neighborhood of A, N at A, is B and F. What is the neighborhood of B? I will go to B. I have A, F, E, and C. So A, C, E, F. What is the neighborhood of C? We have D, E, F, and B. And what's the neighborhood of D? We have only C. What is the neighborhood of E? This is E. We have E to C, E to B, E to F. So it will be C, B, F. And that's B, C, F. Neighborhood of F. We have F to E, F to C, F to B, F to A. So it will be A, C, E, F. And the neighborhood of C also will be 4. So you can see that the neighborhood also gives us the idea of the degree. Because remember, the degree of vertex F is 4. Now, when you look at the neighborhood of F, we also have 4 elements. Because the adjacent, the edges that goes from there to other vertex. So now let's look at graph H. The degree of A will be 1, 2, 3, 4. So that's 4. Now the degree of B, you see that B, we have 1, 2, 3, and also we have a loop. A loop is 2, and we have 3 lines, so it will be 5. So the degree of B, to the right also we have 1, so it's 6. So we have B, to the right is C. We have 1 to D, 2, to E, 3 to A, 4. So we have 4 lines. Plus the loop is 2. So that will give us 6. Then degree of C, C is only 1. The degree of D, we count 1, 2, 3, 4, 5. There's no loop. Actually, we have only one loop, which is the vertex B. Now, if I'm looking for the neighborhood of A, then I'll get E, D, and B, because we can see E connect, D connect, B. So neighborhood of A will be BDE. Now, neighborhood of B, we get C, A, and D. So neighborhood of B will be A, B, C, D, E. I missed one. Oh, to my right. So we have B, C, A, D, and E. And since it's a loop, we have B by itself also. So that's why you have A, B, C, D, E. Neighborhood of C will be only B connected. And then neighborhood of D, we get E, B, and A. So we get A, B, E. And neighborhood of E, we have D, A, and B. So neighborhood of E will be ABD. So that's a good example for what is neighborhood, which is also the adjacent, and also what's the degree of a vertex. So degree of a vertex in undirected graph is the number of edges connected. And neighborhood will be the vertex that are connected to the vertex that we are looking for is neighborhood. So with degree of freedom, we use a theory called the handshaking theorem. The concept of handshaking theorem is that if we have an edge, at least in order to get edge, we have to have 2 vertices, which we connect at end point of the edge. So we came up with a theory of handshaking theorem, which says that 2m is equal to the sum of all the degrees in vertex. Why 2m? Because every edge have 2 endpoints. So that's why we say 2m equal to the sum of the degree. Because if we are counting the number of the total degrees of the whole graph, we are going to double it. If we are going to count the number of edges in a graph, we are going to double it because one edge have 2 endpoints. So that's why we use 2m equal to the sum of all the degree. Here we are looking for the number of edges. So number of edges will be the sum of all the degrees of the graph divided by 2, because 2m equal to sum of everything. So yeah, they say proving it is that we say that each edge will contribute twice to the degree count of all vertices. As we said, the edge is the line. It has 2 endpoints, to the left and to the right. So anytime we have an edge, we have to connect to at least 2 vertices. And if it's a loop we count it twice. That's why we can't loop twice. It's connected to the same vertex, but it goes and comes back. So that's why the proof here is saying that each edge contributes twice to the degree count of all vertices. Hence, both the left hand and also the right hand side of this equation equal twice the number of edges. So since again an edge always have 2 vertices connected, is to be 2m equal to the sum of the graph vertex degree, or I would say the degree of the vertex of the graph, the sum. So yeah, they say we should think about the graph where the vertices represent the people at a party and an edge connect 2 people who have a shaking hands. So we see that when we connect two people with an edge, that's why we say the edge will divide by 2, the degree. So we now give 2 examples illustrating the usefulness of the Handshaking Theorem. So let's see the first example. How many edges are there in a graph with 10 vertices of degree C? 6. So this means we have 10 vertices and each vertex degree is 6. So how many edges are there in a graph with 10 vertices of degree 6? Well, I cannot say the answer will be 60 because I'll say, okay, they are the number of edges and each vertex, we have 10 vertex. Each vertex have what? An edge. But we know that the degree of the vertex is 6, which means each vertex has 6 edges. So we cannot say, okay, the answer will be 10 times 6 because we know that each edge will contribute to have to be connected to 2 vertices. So since each edge will be connected to two vertices, we are going to use the handshaking theorem. So it will be 2 times m, which will be the number of edges I'm looking for, equal to the sum of the degree of vertices in the graph. So you get 2m times 60. 60 is the sum of all the degrees because again, we have 10 vertices. Each vertex have degree of 6. So the sum of all the degrees of the vertices will be 6 times 10, which is 60. But remember handshaking rule, so it will be 2m equal to 60 because each edge have 2 endpoints with vertex. So one edge will have 2 vertices equal. So the answer will be 30. So 2m equal to the sum of the degree of vertices in the graph. In this case, we have a graph with what? 10 vertices, and each vertex will have what? 6 edges, degree of 6 edges. Now, let's say the second example. If a graph has 5 vertices, we say a graph has 5 vertices. Can each vertex have degree of 3? Of course, no. Remember, the vertex have to be a whole number. It's like I have 2 children. I cannot have 2.5 children, or I cannot have 2.9 children. Either have 2 children or 3 children. So that's why this will not hold. 5 by 3, the decimal value will come in. It's not a whole number. So that's why the question is, if a graph has 5 vertices, can each vertex have a degree of 3? No. So solution, this is not possible by the handshaking theorem because the sum, first of all, the sum will be what? 15. So we say 2m equal to 15. And m will give me 15 divided by 2, which will give me 7.5. So it's impossible. And actually here, anytime the sum of the degree of vertices is a odd number, then it's not possible because if you divide a odd number by 2, you get a decimal value. So first thing we do here is to find the sum of degree of the vertices in the whole graph. And here the question said 5 vertices, each vertex have 3 degrees. So the sum will be 15. Since it's an odd number, then we cannot do that. It's impossible. It cannot have a degree of 3. So the second theorem here saying that an undirected graph has an even number. It has an even number of vertices of all degree. So the proof here is that if we have V1 and we say V1 is the vertices of an even degree and V2 will be the vertices of odd degree in an undirected graph, then we can say that 2m, m again is the number of edges, so 2m equal to the sum of the degree for V, which will give me the sum of degree of V when V belongs to only V1. Remember, V was the whole thing. Now we divide V into V1, V2. So it will be the sum of the degree for V1, that is the degree of vectors for V1, plus the degree of vectors for V2. Here, first we have V belongs to V, but this time V is break into V1 plus V2, or V1 and V2. So we have to add V1 and V2 together to get V. So now we move on to the directed graphs. We can record the definition of a directed graph in our first lectures, 10-1. And directed graph G, which consists of vectors and edges, V and E, always there will be a direction. The direction, let's say that we have a vectors U and V. A directed graph means the edge will give a direction, whether we are moving from V to E, or V to U or U to V. They will give us the direction. So an directed graph, a directed graph, G equal to V and E consists of V, is a non-empty set of vertices or nodes, and E is the set of directed edges or arcs. Each edge is an ordered pair of vertices. So it's the same rule as undirected graph. Each edge we have two endpoints. So we're going to have two vertices. But the thing we have to say here is that a directed graph, we will show the direction where the edge is moving, whether it's moving from U to V or V to E. So if we have a graph with vertex UV to be an edge in G, then U is the initial vertex of the edge and is adjacent to V, because vertex UV is connected by one edge. So U is adjacent to V, or V is adjacent to U also. So when we have a directed graph, as we can see here, some arrow will be showing the direction here we are moving from A to B. Another arrow will show from, A to C. Another arrow will show from C to A. So the direction is very important. So here we say we have what we call the in degree of vertex. In degree means the edge is moving towards the vertex. So if I'm moving from A to C, I would say I have in degree for a section. Now, out degree means I'm moving, if I'm in a place of vertex A, then I'll say I have out degree from A to C. The direction is moving from A to C. But if I'm still at A and I want in, I will say that I will use the E. The E to the left side is moving from E to A. So in degree means the direction is moving towards your vertex. Out degree means the direction is moving from your vertex to, again, another vertex. So that's why we have, and also we should know that if we have a loop, we have to contribute for both in and out. So it's to be two. So that's why note that a loop at a vertex contribute one to both the in degree and also the out degree. So here we want to know the in degree of A. So when I look A, I can see the in degree will be, the loop is 1, and from E to A is also 1, so I have 2. The out degree for A will be from A to C, from A to B, from A to E, and also the loop. So the out degree will be 4. So let's say the out degree for A. Yeah, so right here, the out degree for A is 4. Because we can see right here, the loop is 1. From A to B is out. From A to C also is out. And from A to E also is out. Plus the loop, that gives me 4. So what about the in degree or an out degree for B? So first, let's say the out degree. Out degree means we are going out from B. So we have 1, and I think that's it. So the out degree will be 1, which is plus, degree plus is 1. Now the in degree for B, we have C to B, A to B, and I think that's it. So in degree for B will be 2. And let's see, in degree for B, yes, it's 2. Now in degree for C is 3. So let's see why C is 3. The loop is 1, and we have from C to A and C to B. So that's 3. C to D actually is D to C. The direction show D to C, not C to D. So that will give us 3. And let's do one more out degree. Let's say out degree for B and C. So out degree for B, we have 1, only 1. So our degree for B equal to 1. That's correct. And for C, they say 2. Let's see. C, the loop is 1. And also, this is our degree. So we have from C to B. So it's only 2. C to B. C to A, actually it should be A to C. It's going direction of A to C. And D also, D to C is going direction D to C. So C to B is the correct answer. And also 1 loop, so that will be 2. So let's look the out for C, and that's correct, it's 2. So out for D is also 2. Let's see why is it 2. Out for D is here, we have D to C, and we have D to E. And D to second E is opposite, to B is also opposite, so same thing. So here we say Theorem 3, let G again be the vertex and edges of a graph, but this time with the directed edges. So if we have a directed edges, the total edge will be the sum of the degree in and degree out divided by 2. Because remember, the edge always contribute to 2 vertices. So the best way to say it, according to the theory here, the edge will be the sum of the degree in, which is the same as the sum of degree out. So the first sum counts the number of outgoing edges over all the vertices, and the second sum will count the number of incoming edges over all vertices. And this follows that both sums equal then the number of edges in the graph. So number of edges will be the sum of the degree in or degree out. So these are some of the special types of simple graphs. These are called the complete graphs on n vertices. Will be denoted by Kn. Is the simple graph that contains exactly 1 edge between each pair of distinct vertices. So you can see we have K1 is only 1, nothing is connected. But from 2 going K2, we have 2 edges at the end point. And 3 edges again, 4, etc. So the list keep going. And also we have what we call a circle CN, a circle graph. A circle graph means the number of vertices or the edges should be 3 or more. So we can see how we get our 3 first, then we go 4, 5, etc. And these are again special types of graphs. Also, the wheel can be obtained by adding an additional vertex to a cycle or a circle CN for n greater than or equal to 3, and connecting this new vertex to each of the n vertices in Cn by new edge. So an n-dimensional hypercube or n cube, Qn, is a graph with 2 to the power n vertices, representing all the bit strings of a length n, where there is an edge between the two vertices that differ in exactly 1 bit position. So you can see Q1, we have 2 vertices, 1 edge. Q2 is 2 to the power 2, so that will be 4 now. So the possible combination 0, 0, 0, 1, 1, 0, 1, 1. That is 4. 2 to the power 3 will be 8, so this should give us 8. 1, 2, 3, 4, 5, 6, 7, 8. We also have a special type of graph for computer network application. For example, the first one is the computer network application called the star connection. So in the star, we have a central hub, and that is connected to all the possible nodes. Then we also have the ring token algorithm. This algorithm is done by IBM. You can only transmit data. This is computer network, so transmission of data. So you can only transmit data in this section when you have what we call the token. If you don't have the token, you cannot translate data. Then we have the mesh tab. Mesh tab means all the computers are connected to each other. So the vertices here are computers. So those are the 3 basic computer network topology or physical connection. Either it can be star connection, which means we have a central hub in the middle connected to all the devices around it. Or we may have a ring, all the computers are connected in a circle. You can only transmit information if you have that ring. Then we have the merge. So here we say some local networks use the star topology, which is a complete bipartite graph, K1 and N, as shown in figure A. So this is our star topology computer network. All devices are connected to the central control device, which we call the hub. So only other local networks are based on a ring topology, where each device is connected to exactly 2 others using CN as illustrated in B. We also have what we call the bipartite graphs. So here, if we have a simple graph G and is bipartite, if only V can be partitioned into 2 disjoint subsets V, 1 and V2. So that's why it's called bipartite. Bi means 2. You have a graph and you break it down into equal parts of 2, V1 and V2, such that every edge connects a vertex in V1 and also a vertex in V2. In other words, here we say there are no edges which connect 2 vertices in V1 or V2. Also, it is not hard to show that an equivalent definition of a bipartite graph is a graph where it is possible to color the vertices red or blue so that no, again, distinct vertices are the same color. So the whole concept of, again, bipartite graph means we have one graph, we break it into 2 equally, and each element in each graph will be connected to each other. So this is an example here. They say we should show that C6 is bipartite. So we can partition the vertex set into V1, V2, 3, 5. V1, V3, 5. And for V2 is V2, V3, V6. So that every edge of C6 connect to a vertex in V1 and V2. We can also show that C3 is not bipartite. That's if we divide the vertex set of C3 into 2 non-empty sets, one of the two must contain two vertices. But in C3, every vertex is connected to every other vertex. Therefore, the two vertices in the same partition are connected. So these are some of the complete parted graphs. We say a complete parted graph K, M, and N. M and N is a graph that has its vertex set partitioned into two subsets, V1 of size M and V2 of size N, such that there is an edge from every vertex in V1 to every vertex in V2. So this is an example of a bipartite graphs. So the definition here said a subgraph of a graph G, which consists of vertices and edges, is a graph WF where W belongs to V and F belongs to E. Example, they say here we show K5 and one of its subgraphs. So let G vertex and edges be a simple graph. And the subgraph induced by subset W of a vertex set V is the graph. So WF, where the edge set F contains an edge in E, if and only if both endpoints are in W. And this is another example for bipartite graphs and matching. So here we say again, bipartite graphs are used to model applications that involve matching the element of one set to element in another. So we have example for job assignment. Vertices represent the jobs, and employee edges link employee with those jobs that have trained to do. So vertices represent the jobs and employees, and edges link employees with those jobs they have been trained to. The common goal is to match jobs to employees so that the most jobs are done. So here we have a requirement, architectural implementation testing. Here we have 4 students. And also the aftermath, we also have 4. Another example can be a marriage. So vertices represent the man and the woman, and edges link a man and a woman if they are an acceptable spouse. Then we may wish to find the largest number of possible marriages. We also can have a new graph from old graph. So the definition is about union of two simple graphs, G1, G2, is the simple graph with vertex V1, union V2, and edges U1 and U2. So we can see an example here. If you look at vertex G1, we have some set and G2 also. But we can join the two together and we remove the duplicates and we get a union of G1 and G2. So again, this will be the conclusion of our lectures in graph theory, and this is lecture chapter 10, section 2. Again, wish everybody the best and thank you.